That asteroid is not turning once, it is turning twice. One slow roll, one hidden wobble, both happening right now in the dark. And a small NASA probe is the reason we suddenly know. If real space stories pull you in harder than science fiction, subscribe now and stay close, because the truth behind this one gets stranger with every step. A headline like this sounds too dramatic at first. Something in space is found and the world stops. But sometimes that is exactly what happens. Not with sirens and panic, but with silence. People stop scrolling. Scientists stop and stare at the data again. The old picture in their heads cracks a little. That is what NASA's Lucy mission did when it took a close look at an asteroid named Donald Johanson. The name sounds quiet. The object looks small. Yet what Lucy found there forced experts to rethink how a simple rock can move, how it can age, and what it can still hide after millions of years. And the wild part is this was not even Lucy's main target. This was a practice run, a warm-up, a rehearsal before the real show starts near Jupiter. So if a rehearsal already changed the story, what happens when Lucy reaches the objects it was actually built to see? To understand why this matters, we have to go back a little. Lucy launched on October 16, 2021. Its goal is one of the boldest in space exploration. It is going after the Trojan asteroids, a huge group of ancient space rocks that travel around the Sun in the same path as Jupiter. These asteroids are not close to Jupiter itself. Think of them more like runners on the same giant track, one crowd ahead of Jupiter and another crowd behind it. Scientists care about them because they may be some of the oldest and best-kept leftovers from the early solar system. In simple words, they are time capsules. They may still hold clues from the age when the planets were forming, crashing into each other, and moving into the places where we see them now. Lucy is the first mission ever sent to study this strange family up close, and that alone would make it historic. The spacecraft is expected to visit a record number of asteroids. Over its long journey, it will fly by 11 objects. Some are in the main asteroid belt between Mars and Jupiter. Others are the Trojans, the real prizes waiting farther out. NASA named the mission after the famous fossil called Lucy, the ancient human ancestor found in Ethiopia in 1974. That fossil helped change the story of where we came from. The spacecraft Lucy is meant to do something similar for the story of the solar system. Even the names along this mission tell a story. The first asteroid Lucy visited was called Dinkinesh, which is also the Ethiopian name linked to the Lucy fossil. Later, it flew past Donald Johanson, named after the scientist who found that fossil. So from the start, this mission carried a message. We use one Lucy to understand our past on Earth, and another Lucy to understand our past in space. But before Donald Johanson shocked people, Lucy had already given scientists a warning. On November 1, 2023, it flew past a tiny asteroid called Dinkinesh. This object was only about half a mile wide. That is small enough to sound almost unimportant next to planets and moons. Scientists expected a small rock and a short test. They wanted to make sure the cameras, sensors, and timing all worked before the bigger targets came later. A simple pass, a simple picture, then move on. Instead, Lucy found that Dinkinesh had a tiny companion. Not just any companion either. It had a strange little moon called Salam. And Salam itself turned out to be a contact binary, which means two small pieces touching each other like a dumbbell or two snowballs stuck together. Right there, on a warm-up flyby, Lucy had already found something nobody expected to see first. That Dinkinesh encounter mattered for more than one reason. Scientists had believed such a tiny asteroid would be fairly simple. A small body, a rough surface, maybe a few craters, not much else. What Lucy actually found was a much more active history. Dinkinesh showed a trough, which is like a long, low cut in the surface, and a ridge, which is like a raised line of piled-up material. It looked like the asteroid had gone through stress, breakage, and change. Researchers think sunlight slowly changed the way Dinkinesh spun. That spin built stress over a long time. Then, a big piece of the asteroid may have shifted, throwing debris out around it. Some of that debris fell back. Some may have helped form Salam. So even before the famous later discovery, Lucy was already sending one clear message. These rocks are not dead little stones. They have stories. If a half-mile asteroid can hide a tiny double moon and a violent past, what do you think a larger target might be hiding? Tell me what surprises you most so far, and if you like real space mysteries, hit like and subscribe. By the time Lucy set its course toward Donald Johanson, scientists were alert. They knew the mission could surprise them. But they still had a working idea in mind. Earth-based telescopes had watched this asteroid from far away and measured the way its brightness changed over time. That brightness pattern suggested an elongated object, meaning one that was stretched out rather than round. The light seemed to repeat on a cycle of about 10.5 Earth days. So the picture in many minds was simple. Donald Johanson was probably a long asteroid slowly spinning. That would still be useful science. Lucy's flyby on April 20th, 2025 was meant as a dress rehearsal before the first true Trojan encounter in 2027. The team wanted to practice everything at high speed and learn how the spacecraft handled a close pass. A solid test, good images, better preparation. That was the plan. Then Lucy got close. The spacecraft passed about 650 miles from Donald Johanson. That is around 960 kilometers. In everyday terms, that is roughly like flying from one big city to another on Earth and missing by only that distance, while moving through space at incredible speed. Lucy was racing at about 30,000 miles per hour during the encounter. At that speed, every second matters. Every command matters. The cameras have to point at the right place at the right instant. There is no slowing down, no circling back, no second chance. The first close images came in, and right away scientists saw this object was not just a stretched rock. It looked like two lobes joined by a narrow neck. A bilobate shape, they call it. In plain English, it looked like a peanut. But even that did not capture how odd it was. The neck between the two larger parts looked strange, almost like two ice cream cones pushed into each other tip to tip. This was the first big crack in the old idea. Scientists expected an elongated body. What they actually saw looked more like two pieces that had once been separate and later came together gently. That matters because shape is history in space. A crater tells you about an impact. A ridge tells you about motion. A double-lobed body can tell you about a collision, a breakup, and then a quiet meeting under weak gravity. In other words, Donald Johanson may be a fragment from a larger asteroid that smashed apart long ago. Then, two pieces slowly drifted and settled together. Not a smooth birth, not a calm life, more like a wreck that rebuilt itself. And remember, this was supposed to be the simple part of the mission. Lucy's early data also showed that Donald Johanson was larger than many scientists first thought. The first measurements suggested it was about 5 miles long, or 8 kilometers, and about 2 miles wide, or 3.5 kilometers, at its widest point. That may not sound huge, but for a close flyby target, it is large enough to matter. It was also so large in Lucy's view that the full asteroid did not fit neatly inside the first high-resolution images. Even the camera's field of view was not enough to grab the whole shape at once. So the team had to wait for more data to come down from the spacecraft. That delay added tension. They knew they had something unusual, but they did not yet have the full body in one picture. And when the fuller picture formed, the mystery only got deeper. Here comes the detail that made many researchers sit up straight. The team expected one clear spin, one body turning around one main axis. That is how most people imagine a spinning object in space. But Lucy's data showed something else. Donald Johanson is not just rotating, it is also wobbling. It turns end over end once every 10.5 Earth days, but it also rocks back and forth around its long axis once every 26.5 days. Imagine tossing a top that does not spin smoothly. It rolls, but it also sways. It never looks fully settled. That is closer to what Lucy found. For a rocky body drifting through space, this is a big clue that something important happened in its past. Did you expect a small asteroid to move like a bad thrown top instead of a clean spinning ball? Drop a comment with your guess before we go deeper, and if you want more stories where the real data is weirder than the movie version, subscribe. This two-part motion matters because it tells scientists the asteroid is not in a calm, simple state. Something about its shape, its past collisions, or the way sunlight acts on it has kept it from settling into the cleaner spin many objects show. A 10.5 roll is already slow. A 26.5 wobble on top of that is even stranger. These are not random numbers. They are clues, almost like fingerprints left by old events. When scientists see motion like this, they do not just say, "That is odd." They ask, what force did this? When did it start? And what does it reveal about the inside of the asteroid? That is where Donald Johanson stopped being just a practice target and became a real puzzle. Now we get to one of the most surprising parts of the whole story. Most people think sunlight only lights objects up or warms them. That seems reasonable. Light falls on a rock, the rock gets warmer, end of story. But in space, sunlight can do more. There is a small effect called warp. The full name is long and forgettable, but the idea is simple. When a lopsided asteroid absorbs sunlight and then gives that heat back off as infrared light, it gets a tiny push. One tiny push means almost nothing, but millions of tiny pushes over millions of years can change the way the asteroid spins. So sunlight is not just painting these rocks with brightness, it is quietly touching the steering wheel. Scientists think Donald Johanson once spun much faster than it does now. The estimates suggest it may have rotated at least 10 times faster when it first formed. Over time, the sun's gentle but non-stop push likely slowed it down. That slowdown may have happened over the last 20 to 60 million years. In human terms, that is impossible to picture. In space terms, it is long enough for small forces to become life-changing. As the spin slowed, the balance on the asteroid changed. The force that had been trying to fling loose material outward became weaker. Gravity, weak as it is on a small body, had more say. That means rocks and dust could start to slide down slopes and collect in new places. This helps explain why Lucy saw worn-down craters and ridges on the surface. Scientists expected impacts, of course. Every asteroid has scars. But the surface did not just look beaten, it looked reshaped. Loose material may have slowly moved across the asteroid as its spin changed. So a crater made by one event could later be softened, partly filled, or changed by another process that had nothing to do with a fresh impact. That makes Donald Johanson feel less like a frozen museum piece and more like a place with weather, except the weather is sunlight, heat, motion, and time. It is a reminder that in space, even a tiny rock can keep evolving long after it forms. And then came another reveal, one that pushed this story even further. Lucy's instruments detected signs of iron-rich clay minerals on the asteroid's surface. Clay in space matters because clay often points to water. Not flowing rivers or blue oceans, not anything like that, but some kind of past contact with liquid water. That shocked people because Donald Johanson is a small asteroid and a relatively young fragment, around 155 million years old. Scientists did not expect a fresh clue connected to water to show up in such an object in this way. But the details of that clay made the story even sharper. Here is the difference scientists noticed. On asteroids like Bennu and Ryugu, which were studied by earlier missions, researchers found magnesium-rich clays. Those usually suggest longer contact with water, possibly over very long stretches of time. On Donald Johanson, Lucy found signs of iron-rich clay instead. That suggests the contact with liquid water may have been brief. Water was there, but maybe not for very long. It did something, then it was gone. That difference sounds small, but it changes the history. Two asteroids can look related and still come from very different conditions, different places, or different moments in the solar system's early story. So Lucy was not just finding facts, it was separating cousins who grew up in different worlds. When you hear that a dry-looking asteroid may carry a memory of water, what is the first thing you picture? Tell me in the comments. And if these quiet clues are your kind of mystery, leave a like and stay subscribed. Now let's compare the old expectation with the new picture in a simple way. Scientists thought Donald Johanson might be a useful sample of a small, elongated asteroid in the main belt. Good practice, good images, helpful data. What they found was a strangely shaped, double-lobed body, larger than expected, rotating in two different ways, showing signs of surface change over time, and carrying mineral clues tied to past water. That is not a small difference. That is a rewrite. Each new layer made the asteroid less simple, not more. And when science gets harder instead of easier after better data, that usually means you are very close to something important. There is also a time story hidden in all this. Donald Johanson is thought to have formed about 155 million years ago after a violent collision. That makes it much younger than Bennu and Ryugu, which are believed to have formed around 1 to 2 billion years ago. So on one hand, Donald Johanson is younger. On the other hand, it still carries signs of a complex life. That tells us age alone does not decide how simple an object will be. A younger asteroid can still be twisted by sunlight, reshaped by loose material, marked by impacts, and linked to water history in unexpected ways. In short, it had less time than some others, yet it still became weird. Location matters too. Bennu and Ryugu drifted into orbits that bring them near Earth. That made them easier targets for sample return missions. Donald Johanson stayed in the main asteroid belt after it formed. So scientists had a chance to compare objects that may share some roots, but lived very different later lives. One stayed in the busy belt between Mars and Jupiter. Others wandered inward toward Earth's neighborhood. That is like comparing siblings who spent their lives in different countries, under different weather and different dangers. Similar starting points do not guarantee similar endings. This is how origin stories become clearer, not from one object alone, but from contrasts. And that is why people use the phrase that the discovery stopped the world. Not because Earth was in danger, not because the asteroid changed direction toward us. Nothing like that happened. The world stopped because a small spacecraft turned a practice target into a challenge. A thing many expected to be straightforward became layered, active, and full of clues scientists did not know were waiting there. Moments like that are rare. They do not happen every week. A whole field can spend years building ideas, then one close pass by one machine shows the universe has been holding back a better answer. That kind of shock is quiet, but it is real. Now the story shifts from what happened to what is happening. Lucy is still out there right now, still moving, still sending humanity deeper into a part of the solar system no spacecraft has explored this way before. As of 2026, mission scientists have already begun testing Lucy's cameras for the next and most important stage. The spacecraft has turned its high-resolution camera toward future Trojan targets from hundreds of millions of miles away. From that distance, the asteroids are only pinpricks of light, tiny points, barely more than bright dots. Yet even these early views help the team choose the best camera settings for the close flybys that begin in 2027. That means the most dramatic part of Lucy's mission is not over. It has barely started. The targets now being watched include Euripides, Polymele, Lucas, and Orus. 2 of those are known to have small moons. Lucy is learning how these objects look under lighting conditions more like what it will see during real flybys. That may sound technical, but it matters a lot. Telescopes on Earth usually see the Trojans from roughly the same direction as the Sun. That makes them look almost fully lit, like a full moon in the sky. Lucy will not see them that way during close approach. It will sweep past from different angles, with parts of the surface in shadow and other parts brightly lit. So the team is practicing now to avoid images that are too dark, too washed out, or timed wrong at the most important moment. And the flybys will be fast. When Lucy reaches these objects, it can pass them at speeds up to about 16,000 miles per hour. At closest approach, the spacecraft may come within 300 to 600 miles. That is close enough to reveal major details, but far enough that timing has to be nearly perfect. Again, no second pass, no hovering. Lucy gets one shot each time. Which means what it learned at Dinkinesh and Donald Johanson is not just interesting science, it is training. It is proof that the spacecraft can perform under pressure and still return discoveries nobody planned on. If the rehearsal gave us this much, what will the main event give us? If you could choose the first Trojan Lucy sees up close, which one would you pick to uncover the biggest secret? Write the name you want to bet on, and subscribe so you are here when the answer arrives. The Trojans matter because many scientists think they are ancient leftovers from the early solar system. They may have formed when the giant planets were still moving around, pushing and pulling smaller bodies into new paths. In simple words, they may remember a time the solar system itself no longer clearly shows. They are like dusty rooms no one has opened in billions of years. That is why Lucy is so important. It is not just visiting rocks. It is testing old ideas about how planets formed, how material moved, and how the worlds we know today ended up where they are. And if Donald Johanson already upset expectations, the Trojans may do much more. The first major Trojan encounter is set for August 2027, with Euripides and its small moon Cata. After that come Polymele and its moon in September 2027, Lucas in April 2028, and Orus in November 2028. Much later, in 2033, Lucy is expected to reach Patroclus and Menecius, a remarkable pair that circle each other. That means the mission stretches across years, not weeks. It is a slow story, but a powerful one. Each encounter adds a chapter. Each chapter can test ideas born from the last. And now, every scientist on the mission knows one thing for sure. Do not expect simple answers just because the object looks small from far away. That lesson may be the biggest gift Donald Johanson gave us. Before Lucy got close, the asteroid was a light pattern in a telescope. After Lucy, it became a body with a shape, a wobble, a surface history, and a clue to water. That transformation is easy to miss from the outside, but this is what space exploration often is. You go from a dot to a world. Not a world with trees and air, but a world with its own rules, scars, and past. A dot can fit inside a number on a chart. A world can break your theory, and science grows when dots become worlds. There is another reason this matters for us on Earth. The more we learn how asteroids are built, how strong they are, how they break, and how their motion changes, the better prepared we are for the future. Not because Donald Johanson threatens us, it does not. But one day, humanity may need to move or deflect a dangerous asteroid. To do that, we have to understand what these bodies are really like. Are they solid? Are they loose piles? Do they split easily? Do small forces change their spin over time? Those questions are not only about curiosity, they could become questions of safety. So even a distant practice target can teach lessons that matter here at home. And there is a deeper emotional reason too. Humans have always looked up and asked the same kind of question. Where did all this come from? Not just Earth, not just life, everything. The Lucy mission speaks to that hunger in a beautiful way. The fossil Lucy helped us understand our ancient family story. The spacecraft Lucy is helping us understand the ancient family story of planets, moons, and asteroids. One looked back into human origins, the other looks back into cosmic origins. Different scales, same desire, to know what came before us. Think about the chain of names for a second. Donald Johanson discovered the fossil named Lucy. NASA named the spacecraft Lucy. Then that spacecraft flew past an asteroid named Donald Johanson. A human story and a space story loop together. A fossil from Ethiopia and a rock in the asteroid belt are now linked by one mission. That is part of why this feels bigger than just another flyby. It connects curiosity across fields, across years, across the distance between ancient bones and ancient stone. It feels almost poetic, but the science underneath it is hard and real. The next part is what stays with me most. Lucy was never sent to Donald Johanson as the final destination. The asteroid was a checkpoint, a useful stop, a way to test the hardware and sharpen the team. Yet the universe did what it often does. It took the side road and filled it with something unforgettable. A wobbling, peanut-shaped asteroid with a strange neck, evidence of a violent birth, signs that sunlight slowly changed its spin, surface features that may have shifted over time, mineral hints tied to water. That is a lot of story hiding inside one so-called extra stop. And if that happened before Lucy reached its true targets, we should be careful with every prediction from here on. Scientists will still make their best models. They have to. That is how missions work. But confidence now comes with humility. Dinkinesh and Salam already surprised them. Donald Johanson surprised them again. The Trojans may be ready to do it one more time, or 10 more times. The smart expectation now is not that the mission will confirm everything. It is that Lucy will probably force changes. That is the kind of mission people remember long after it ends. Do you think the Trojan asteroids will turn out calmer than Donald Johanson, or even stranger? Leave your answer below. Give this story a like if it changed how you see asteroids, and stay subscribed for the next reveal. We are also living in a moment when space headlines spread faster than the science itself. A dramatic line can race around the world in seconds, but behind that line are years of planning, patient work, and careful checks. That is why I love this story. The headline is loud, but the truth is better. A small spacecraft launched in 2021, crossed millions of miles, practiced on a tiny asteroid, then found a mystery rich enough to challenge old ideas. No aliens, no magic, no fake drama needed, just the universe being more creative than our first guess. Right now, Lucy is still moving toward the outer part of its path. Right now, engineers and scientists are still preparing for the close Trojan encounters. Right now, the mission is still open, still unfinished, still dangerous in the way all hard exploration is dangerous. One bad timing error or one camera setting mistake during a high-speed pass could cost precious data. But every earlier success makes the team better, and every surprise makes the mission more valuable, because surprises are where the hidden truth lives. That is why this story is still alive today. If you zoom all the way out, the real message is simple. The solar system is not neat. It is not made of clean categories where one asteroid type behaves one way and another behaves another way forever. Even a small object can have a violent birth, a strange shape, a double motion, a changing surface, and a faint memory of water. Even a practice target can become a scientific event. The old image of asteroids as boring leftover rocks keeps failing. Lucy is helping break that image apart. And once that picture breaks, a better one can replace it. So no, the world did not stop because a giant rock was coming for us. It stopped because a machine the size of a small car reached a tiny target and found that our neat story was too small. That kind of stop matters. It is the pause before understanding grows. The breath people take when the facts become bigger than the simple version. In that pause, science gets more honest, more humble, more exciting, and we get to witness it almost in real time. If you want to keep following this mission as the biggest encounters get closer, subscribe, turn on notifications, and tell me in the comments which Lucy target you think will shock scientists most. Then share this with someone who still thinks asteroids are just boring rocks drifting in the dark. Thanks for watching. I'm glad you took this journey with me. See you in the next mystery.